Okay, looks like we are working just fine. Um, okay, welcome. So today we're going to go look at the Advent of Code Day 3 Part 2. Um, and I guess we could try to rehash a little bit of the previous one, but we'll try to dig this challenge up easier. So you were given a bunch of binary values. This is what the real data set looks like, a bunch of 32-bit values. And we need to count the zeros and ones of all the values. So for this part two, we create multiple subsets of the number. So we count the first zero and ones. The most common is going to be the first bit of the oxygen generator rating, and this are the least common is going to be part of the CO2 scrubbing rating. And then what we're going to do is take a subset of the remaining numbers and keep and our search group is going to get smaller and smaller every time. We're going to create a mask as we go along. So let's see how well we can start hacking at this. So the criteria is right here if you want to reread it. But so first let's uh, and I want to know what the length of. Okay, so we just have 1,000. Um, so we're going to have a mask. Current mask. And it's gonna be 0. And C. So we're going to create a mask as we read along, and if something doesn't fit the mask, we're going to ignore it. So we're going to have oxygen and CO2. So we're going to have oxy. So start off as 0, and we're going to have CO2 as 0. And now what we're going to do is we're going to do for x in range 32 down to 31 down to 0, -1. Print x. We make it to go down to -1. Way to do that. Okay. Okay, cool. Now we're going to go for value in yeah. If value ended with the with current mask equals oxy. We'll do a quick print add hi. So make sure that invalid certain syntax. You want that? Okay. Um, and then we're going to count most common x bit and count least common x bit. Okay, so we're going to take the x bit of the value, and let's go ahead and just take right here, we're going to look at, so we're basically saying, and we're going to count. This is going to be one count 0, right? Oh, and then we need one count. So we're going to have oxy one count and an oxy size. And we're going to do the same thing for the CO2. And right now, so first let's just do +1. 1 CO2, 2 size, and print oxy size. Oh, right here. Okay, that's what we expect. Okay, so now as we're going through this and creating a bit mask, we need to count the values. Right, so, and so we need to figure out the most common one. So we're counting the ones in that specific bit at that specific time. So for example, let's print out the one count on this one and the size. In the mask at all. See. So we're really not using 32 bits in this situation. We're only using 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. It's only 12 bits wide. We're only doing 12. Can we just right there? Right place. That's kind of optimize the code. Okay, so now we need to create the mask. So what we're going to do is we need to determine if the mask is going to be a 0 or 1, and we need to shift it over. So we're going to update mask. First thing, we're going to take current mask. We're going to and it equal to of this, right? So I'll show you how this works, right? We're going to print current mask, and this is slowly fill in the mask. Turn off the hex of it. This is going to slowly fill in our mask of that what we're going to keep track of. Now we need to update oxy value. And to do this, we're going to take the one count, the oxy one count. And we're going to say if oxy one count is greater than or equal to oxy size divided by 2. Then we're going to take the oxy mask and just add a 1 to that bit position. Otherwise, we'd add a 0, but we don't need to specify that. And now we're just going to do it for the CO2. And that should be it. Okay, now let's print. I want to show you how the size should be getting smaller as we, right? We're down to 2 at the final stage. Well, that's not. Be down to 1. Oh, this is the least common one. Right. So define this to determine the least common value. Keep only the numbers that keep considered. So I think we just gotta do a less than equal to right here. And so we start at 1,000, decrease, decrease, decrease. Okay, yeah, we need to start at the 12-bit. 12-bit. And why are we not getting rid of values? How are we gonna do that? If x is less than 3, print above value 1 ff. Let's print out x, right? Let's see what 0. Way to print out the. Okay, here we go. So we need to figure out that value as well. X is 0. Oh, okay. And then what we need to do is we need to print oxy print CO2. Okay. So we build the values. That makes sense. Okay, we don't print that out. Okay, so that should be our correct value right there. And just need to multiply those together to get what we expect. Huh. Not get the correct value. Okay. Oh, I think it's this the CO2 value is not correct because we didn't stop it. So like if I show you, it's slowly changing here. It shouldn't change. Probably the issue is this value shouldn't change. It's the 0. So we want to say and greater than, right? And oxy size. And still more bits in here, so I don't think that value is. The CO2 size is 1. Print found it. Found it. So they found it there, but we got to figure out. So I mean, We're gonna do. What's the best way to do that? Do we just do a quick sample, or we just grab in the next value? I don't know. How do we end the search pretty early? CO2. To end 0. If CO2 underscore end equals 1, then CO2 equals value. We should probably do that the same thing. This oxy. We should probably just find it right there. And that's not going to work if we get the last round, or depending on. So if it equals 1, we need to find it. So, and we're just going to go through all the things and in the one that matches the mask and assign it to CO2 equals a value. Still not the right answer. Your answer is too high. Find errors in your data report to calculate oxygen generating. Multiply them together. Okay, so figure out what we're doing. So what's the best thing? The best thing is to probably print out the oxy 1 count and the oxy size. And so 0, 0, 0, 0, 0, 1, 40, 6, and 5, over 5, 1 over 3 is 0, 1. Okay, that's it. Find the oxygen range, determine the most common value in the current bit position. That bit. Make sure we're not going the wrong direction. Okay, let's. Okay, so 4, 5, 6, 7. So it's 7 ones. Keep only the 5 bits with. .506, that's right. 30, 26, 60. That looks right. Ugh. You do one count, size, an area of 2. 494, 54. That's gonna be a 0, yeah. Be a 1, yeah. Is 0. Yeah, yeah. It looks right. What could we be doing wrong here? So, and if we switch this to 12, we'll just, right? I thought. 11. Make sure our puzzle input actually is day 3. F value. Yeah, it looks correct. Okay. Um, say that number's 2. What is 2 to the 12? 6? Definitely possible. I mean, it's gonna have to be those. How do we? No, so sure, whatever. Those ones should reflect each other. Okay, let's print and What are we missing? People understood by the bit criteria. Searching discolored numbers, the criteria. Yeah, that's win. Number left, stop. That's ring value. Okay, alright. Positive to the next. Right. Let's see, does that change anything? I think they would. Weird if they would. Okay, it's between those two numbers. Okay, 'Maybe it's this. 5 minutes. We're using 1,000 values. That's right. 1,000. Probably have recorded the number. Oh, the first one was too high. And so we're right there. This one was too high. I'm trying to figure out what to do next. What do we do? I guess we do the samples. We have sample data, right? I guess we sample. Well, 5 bits wide. Let's start here. Okay, well, I guess we'll just solve it with this. Uh, let's see. So bit 4, do this front bit, and 16 and 0. 2 and 5. What's How about right, is there it's even. Oh, else if ah, if guys. Um uh, happening here. One. That should be a 0. Uh okay. So but we didn't activate the search. Where the mask was done. I want to do it before the mask is done. There we go. The mask was getting in the way. If one keeps it. Guess we could just 23 and 10. Okay, so back up here. Down here. 11. 509 and 260. Ah, those numbers see. Okay. Now we're supposed to put this in HLS. I don't. How do we do this in HLS? Can we do a fancy data structure in HLS? Just delete values we don't care about? What's the easiest way? This mask way seems the best because we're just reading, we're not doing additional writes, which are cycles. I guess we just have to implement it the way we have it here. Is there a way we can change how these values are stored? create a tree. Tree might be the easiest story possible. How do we do that? Maybe have to do that in Python to figure that out. Okay, so what I'm thinking is go to market. What we want to do is, right, we want to do that or that many. That's just going to take more data in the end. What's a good way to do this? Do we just do BRAM and we just pass it over? Do we just create an array of 100 and just pass it? That's basically what we're doing here. Flow. We could try to loop unroll it and divide it. Optimize. Okay, well, let's just start whacking it. Array. What if we just say what? Array count. What was that? It's gonna be gamma. Have to. And loop. Three, two. Let's just say inner int idx x equals 0, x is less than 1,000. X plus. And what do you want to say? A we'll just do something very simple. Just want to see something like that. So project settings. What produce? Get rid of that. Why the buttons disappear at the res. Unrolling loop completely. I think it's going to take a lot. It's unrolling a loop of 32, or unrolling a loop of 1,000 inside 32. That's going to be a massive, massive unrolling for the function. Well, may need to turn pipelining off, or just have it discretely take in 1,000 values. We may have to get smarter of our HLS to figure this out, which is good experience. Instead of taking in a single value stream, maybe we should learn how to take in a actual like array. Look up some examples for that. For how long is it? Okay, while we're waiting, I'll probably start doing a GitHub for all these projects, so on them. I start doing better comparisons. May have to set on how to. May have to go and offline try to figure out how to improve this better. But yeah, feel free to join the Discord. Feel free to wait. Bug me about the GitHub projects, GitHub pages, and hopefully we can get something going forward. Get good at what? Get good in general. Play Elden Ring. Maybe we should play Elden Ring through FPGAs. I'll do that sometime. We'll do some FPGA filtering for video games. But yeah, Michael, feel free to join the Discord. Okay. Does that link work? Need to update? You can also try this link. I'll update the YouTube with that forever link. Apparently, you have to add better links to this. Okay. Uh. Hello. Yeah, I need to figure out how to do these voices for the stream. FPJ aimbot. So yeah, we're gonna look at trying to incorporate FPGAs into some video games. We'll see how that goes. Um, for now, we'll just probably do some fun bell filtering. Maybe build up to a neural network that helps you identify targets. But yeah, I this loop unrolling in the HLS is going to be ridiculous. So I'm just going to probably end the stream. Oh, are you actually going to finish this? Yeah, yeah, you're doing something really stupid. So yeah, we're probably going to end the stream now because I'm not even know if this HLS is going to finish synthesizing a solution by the time. So I guess we'll come back to this HLS problem next week, and I'll probably get a better solution in the background. And we can talk through it. The advent of code does provide some pretty fun challenges for HLS I don't think you normally deal with, and it's kind of fun seeing how you have to change your thinking from a software perspective to a hardware perspective. And the reason this part is so challenging is it's doing multiple random memory accesses, which is kind of destroys the parallelism and pipeline you can achieve in an FPGA. So this specific function of like looking at a data list and going back and forth and like slowly crunching down the numbers is actually a lot more useful on a GPU than FPGA. Where you can do parallel processing with multiple processing cores on the same memory. And yes, you can achieve kind of the same architecture on an FPGA, but what the advantage is that you can do a much higher clock rate on a GPU. Gigahertz. We're talking probably 20x speed up on GPU rather than an FPGA. Okay. We'll see. DMA, FPGA accelerated cheat engine. You'll have to. Yeah, that'd be interesting. Okay, well, thanks for joining us. Yeah, if you want to talk in the Discord, shoot up some ideas. We may have, I may invite people to chat during the stream. I have a chat room right now, but I'm not sure how. I want people to know they're being recorded on a stream and not just randomly